Okay, in this video we're going to go through a couple of different integration problems and some differential equations at the very end. This should all be a review from Cal 1. So certainly you got the power rule, then the antiderivatives of the basic trig functions. That's what we look at for here. This one is not one of those, so our thing to try is a U substitution. So if we let U equal the denominator, the t squared plus t minus 4, then du will be equal to 2t plus 1 dt, which is exactly the numerator. And so the goal for the U substitution is to replace everything with t or x or whatever the variable is with expressions of U. Okay, so the top will become du and the bottom will become U. And then that is ln absolute value of U plus C. So ln absolute value of U plus C. And then, of course, we'll replace the U with the t squared plus t minus 4, and then plus your constant integration there. So that's it for that one there. So that's certainly a Cal 1 integral using U substitution. So let's go ahead and take a look at another one. So number 2 here, we're going to integrate 2 over 2t minus 1 squared plus 4 dt. Again, this is not a basic trig function or a power rule, so we're going to look at maybe doing a U substitution here. So the derivative of 2t minus 1 is going to be 2, so we'll look at that and see what that brings us. So U is 2t minus 1, then du is going to be 2 dt. So we're going to at least make that a replacement. So the numerator will become du, and the denominator will be u squared plus 4, and that is exactly the arctan. So this is arctan would be, what did we say arctan was? So if we had du over u squared plus a squared, that was 1 over a arctan u over a plus c. And so in this case, our a is going to be 2. Okay. So we have 1/2 arctan of u over a plus c. So that's going to be 1/2 arctan of u is 2t minus 1 all over 2, and then plus c. Okay. And that's it there. So again, we used some U substitution, and then it turned into something that we recognized as the arctan. Okay. Moving along, here we're going to look at the antiderivative of negative 2x over the square root of x squared minus 4. Again, probably we would like to do some sort of U substitution. If we let u equal the x squared minus 4, the u will be 2x dx. So that looks pretty good. So u equals x squared minus 4. The du will be equal to 2x dx. And so that's looking like a pretty good substitution. We do have that negative sign up there. We can just factor that out. So you can factor constants out of an integral. So that's going to be negative integral of du over the square root of u. And remember, square root of u is u to the 1/2. Now, since it's in the denominator, it's going to be u to the negative 1/2 du. And now this is a power rule, so we're going to add 1 to the minus 1/2, which will make it positive 1/2. And then we're going to divide by that exponent, and then plus c. Okay, so we'll flip that fraction over and change it into multiplication. So that's going to be negative 2 square roots, and then u was x squared minus 4, and then plus your constant of integration. And that's it for that one. Okay. So this was entirely just a Cal 1 integral. Okay, moving along. Here we have the integral of x, and then, integral of 1 over x, and then the square root of x squared minus 4 dx. Okay, this looks a lot like du over u square root of u squared minus a squared, and that's going to be 1 over a arcsecant, or secant inverse, absolute value of u over a, and plus c. So that looks like the arcsecant to me. Okay, where your a is 2, so it's going to be 1 over 2 arcsecant absolute value of x all over 2 and then plus c. So that was a pretty straightforward inverse trig function there. Let me erase this because it looks like we're going to put another example on this slide here. Okay, let's go ahead and continue. So number 5 here we have, excuse me, we have 5 over t plus 6 to the third power dt. Again, it doesn't look like something real basic, trig function, power rule, anything like that. It is going to be a power rule, but we'll probably want to do a U substitution. So we'll let U equal t plus 6. du will be dt exactly. And so this will become, we'll factor out the 5. And then u is the t plus 6, and it's in the denominator with an exponent of 3, so that would be u to the minus 3. And so that's a simple power rule. 5u, add 1 to the exponent to make it negative 2, divide by negative 2, plus constant of integration. So that'll be negative 5 over 2, and then replace the u with t plus 6, and then the exponent will be squared, and then plus your constant of integration there. So that was pretty much Cal 1 integral also. Okay, so let's get a couple more to run through. Number 6, we have 3x over x plus 4 dx. Now, one thing when you have a rational function where you have a rational expression, a polynomial divided by a polynomial, if the degree of the top is greater than or equal to the degree of the bottom, so if the degree of the numerator is greater than or equal to the degree of the denominator, oftentimes we want to do either synthetic division or long division to simplify this down. So we're going to go ahead and do long division because synthetic division is a little bit more specialized. So long division is going to be a little bit more general. So x plus 4 is going to go on the outside. That's your dividend, and then 3x is your 3x is the dividend, x plus 4 is the divisor. So x times 3 will be 3x, 4 times 3 is 12. We'll go ahead and subtract. We'll get negative 12. Okay, so your quotient is 3, your remainder is minus 12 over the divisor of x plus 4. And so now that's pretty easy to integrate. So antiderivative of 3 is 3x, antiderivative of negative 12 over x plus 4, that's just going to be negative 12 ln absolute value of x plus 4, and then plus your constant of integration. Of course, you could do that integral separately, the negative 12 over x plus 4 if you needed to. U is x plus 4, and then du would be equal to dx. We could slide out the 12, and we would be looking at du over u, and we integrated that a little bit a little while ago on one of the previous examples, and that was going to be absolute value or ln absolute value of u plus c. Okay, so what do we got? We got about 4 more to do. Just run through a couple of different varieties of integrals here that we can run into, both Cal 1 and Cal 2 type. And these are kind of like the first of the Cal 2. We haven't gotten into the integration by parts or any of the interesting trig integrals or trig substitution. So that'll come, don't worry. Alright, so we're going to look at the integral of cosecant squared e to the cotangent of x, and then what you should be focusing on is, oh, I know what the derivative cotangent is. It is negative cosecant squared. That looks like what my U substitution is going to be. U is the cotangent of x. du is equal to negative cosecant squared x dx. And you might be thinking, well, I don't quite have the negative cosecant squared x. So let's just go ahead and put a negative, and then we'll put a negative on the outside to offset, so we haven't changed anything. So now we got our good substitution. So now we're looking at negative e to the u du, okay? And e has the nicest derivative and antiderivative. It's going to be itself, okay? So that's going to be negative e to the u plus c. And go ahead and replace the u with the cotangent of x and plus c, and that's it. And then certainly you can take the derivative of that right there, and you get right back to cosecant squared x e to the cotangent of x. So it's a good problem as both a chain rule problem for derivatives, and it's also a good antiderivative. Okay, let's move on to another one. So we're going to look at the integral of 2 over 7 e to the x and plus 4 dx. Okay, and I'm already wanting to do a U substitution. I probably would like to have U be the denominator, but the problem is the derivative of 7e to the x plus 4 is going to be 7e to the x dx, and so I don't have a good U substitution. So we're going to try a trick here, and we're going to multiply the top and the bottom by e to the minus x, and then maybe we can get a U substitution going. So there is just the integrand, and we're going to multiply it by e to the minus x and e to the minus x. So that'll become 2e to the minus x, and then you're going to have 7e to the x times e to the negative x. So you're going to add your exponents, so that gives the exponent of 0, e to the 0 is going to be 1, and then times the 7 there. Okay. And then plus 4e to the minus x. So now I have an e to the x on the top and the bottom. I have I guess it's not quite a binomial, but I have two terms on the bottom. One's a constant, so when we take the derivative, that's going to be gone. And then we have an e to the minus x on the top. The derivative of e to the minus x is minus e to the minus x, and so we'd be off by a constant. That's fine. We can be off by constants. Okay, so there is your new integrand, and we will perform some U substitution. We will let u equal 7 plus 4e to the negative x. Du will be equal to negative 4e to the negative x dx. Okay, so we don't have a negative 4 in the numerator. Well, we can go ahead and fix that, and we can multiply by negative 2 and then divide by negative 2. Okay, so we go ahead and introduce that and then divide by it. So negative 2 as a factor, and then negative 2 as a divisor. Those cancel out. Okay, so we got negative 1/2, and then it's going to become the integral of du over u, and well, that's going to be negative 1/2 natural log absolute value of what is u? U is 7 e to the 7 plus 4e to the minus x, and then plus your constant of integration. You can drop the absolute value bars because 7 is always positive, e to the minus x is always positive, and 4 is always positive. So natural log doesn't like anything that's negative or 0. So 7 plus 4e to the minus x, that's safe. It will always be positive. Okay. At the end here, we're going to look at solving two differential equations by separation of variables. So number 9 here, we have dy over dx is equal to 4 minus e to the 2x quantity squared. We'll go ahead and separate the variables. So we'll have dy is equal to, and I'm going to go ahead and FOIL, 16 minus 8e to the 2x plus e to the 4x dx. And then we'll go ahead and integrate both sides. So the left-hand side will be y. And then we'll have 16x minus, it's going to be negative 8e to the 2x, then we got to divide by 2, so that'll give us the negative 4e to the 2x. And then plus 1/4 e to the 4x, and then plus your constant of integration. Okay. All right, so we're going to look at one more here. So here we have dr over dt is equal to 1 plus e to the t quantity squared, and then over e to the 3t. So we'll go ahead and first separate the variables. So we have dr, and we'll go ahead and FOIL the top, 1 plus 2e to the t plus e to the 2t all over e to the 3t dt. Okay, and then so we'll have dr, and we'll go ahead and split that up. So 1 over e to the 3t is the same thing as e to the negative 3t. 2e to the t over e to the 3t would be 2e to the negative 2t. and then e to the 2t over e to the 3t is e to the negative t dt. Lots and lots and lots and lots of t's. Now we're going to integrate both sides. Left hand side is r, and then we'll have negative 1/3 e to the negative 3t plus, well, sorry, it'll be minus because it'll be 2 divided by negative 2, so negative e to the minus 2t, and then finally minus e to the negative t, and then plus your constant of integration. Okay, so hopefully you found this helpful. This particular section in our textbook is all review, so they're just throwing a bunch of different types of integration at you, and that's the big thing in this chapter is all things integration. So we're doing a little bit of familiarizing ourselves with some stuff that we had back in Calculus 1.